So last week we talked about stationary iterative methods, and those were Gauss-Seidel, SOR, and the Jacobi method. And so those methods were based on just kind of like a fixed point iteration, which you saw when you did solve nonlinear equations. But this week we're going to talk about non-stationary iterative methods. So there's still iterative methods that solve the system AX equals B, but instead of having like a fixed point iteration, they're non-stationary, so the points will actually change. But before we can talk about non-stationary iterative methods, there's a few other things that we need to talk about first. And so one of those things is measuring the sensitivity of a system. So if we are trying to measure the sensitivity of a system, let's consider a parameterized system. So AX equals B, but it's going to have some perturbation. So again, we're starting, of course, with AX equals B because this is the system that we want to solve. So we have A plus epsilon times E x of epsilon equals B plus epsilon times E. And so this is just a perturbation of the system AX equals B, where of course E is given Rn by n, and the vector E is in Rn. And they are perturbations of A and B. What we want to do now is I'm going to take the Taylor expansion of x of epsilon around the center epsilon equals 0. So if you recall the Taylor expansion, now our center, okay, so I'm writing this down. Our center is going to be epsilon equals 0, so that will simplify this a lot. And so if I do Taylor expansion of x of epsilon, f of x equals f of a plus f prime of a times x minus a, and then we have plus f double prime of a over 2 factorial and so on. But here our center is going to be 0, so we just have x plus epsilon times x prime of 0, and I'm just going to go up to the first, and everything else can just be represented by O of epsilon squared. So now I'm going to take a look at x prime of epsilon, but I'm not going to get it from here. I'm going to get it from up here, actually, by differentiating this and then solving for x prime of epsilon. So if I differentiate this, we have to use the product rule first. We would get E, let's see, yeah, differentiation with respect to epsilon. So we have E, derivative copy plus derivative, x prime with epsilon equal to, that's going to be 0, and here we would just have okay. So now I've differentiated this with respect to epsilon, and I'm going to go ahead and solve for this x prime of epsilon right here. So move this term over. A plus epsilon E x prime of epsilon equals E minus x of epsilon. And then I can multiply both of these on the left-hand side by the inverse of this matrix to cancel that. So I get x prime of epsilon equals A plus epsilon E inverse times E minus E x of epsilon. Alright, so now that we've differentiated that with respect to epsilon, or x with respect to epsilon, let's take a look at x prime of 0 now. So just plug in 0. So we get is A inverse E minus EX. So this is going to help us to look at the sensitivity of a matrix. So what I'm going to do now is use norms to measure the relative error in X. And
so what did that tell us, the sensitivity?
Well, no, we're getting there. We haven't really used this yet. But we're going to use this definition. Let's see. When we get to measure the distance between x of epsilon and x, which is going to show us.
So x relative to 0 is just.
Do what?
The epsilon goes away and becomes 0. So. Right. So you don't write x of 0. You just write x dx in the second.
This one right here?
Yeah.
But this is EX is just a function of epsilon. Like all of these are functions. Like everywhere there's an X is a function of epsilon, but it's not actually.
Like if epsilon is 0, there is no epsilon, so just.
Right. So there was no F, but here we had an epsilon, so that's why that term got canceled right there. Okay. So let's take a look. We're going to use norms to measure the relative error in X. And so the relative error is defined by this. So we have X of epsilon minus S all over the norm of X. And so now, if we take a look at this, we've got x of epsilon. So from here, we can pull out an epsilon, and then we have the norm of A inverse E minus E plus X. And so that's where we use this this definition right here that we just defined in the previous board, and this is all over the norm of X, and then we have plus the remainder. So now this is actually going to be less than or equal to, and here I'm just using the triangle inequality. So I've got the norm of A times the norm of E over the norm of X plus the norm of E. Okay, and so we can just use a triangle inequality to end up with this. Now what I'm going to do is multiply and divide by the norm of A. And when I multiply and divide by the norm of A, then I'm going to obviously get the norm of A times the norm of A inverse. And then here, we also divide by A, then I have E, and if I multiply this by the norm of A, then I'm going to get the norm of AX, which is equal to the norm of B, because AX equals B. So we'll just go ahead and replace that with B. And then we have the norm of E over the norm of A here. Okay, so all I did from this point to this point was just multiply and divide by the norm of A. But what I have now is, I'm sorry, I left out my absolute value of epsilon in front there. So what I have now is I've actually defined what we call the condition number. So I'm going to replace this right here. The norm of A times the norm of A inverse is the condition number of A times the absolute value of epsilon times the norm of E over B plus the norm of E over A. And so these were the perturbations that we have on B and A. So this is how we can actually define the condition number. So this is kappa of A is equal to the norm of A times the norm of A inverse. And the condition number is how we measure the sensitivity of the matrix. We want to know if a matrix is well-conditioned or ill-conditioned. So from this, we conclude that the relative errors in A and B can be amplified by the condition number in the solution.
Were we supposed to have the absolute value of epsilon in the second line?
This one right here?
No, up.
This one? No, it hadn't applied the depth. Well, let's see. Oh, yeah, I think so, actually.
Yeah, because you already.
Yeah, because it already was. Sorry. Okay. So the relative error, in A and B can be amplified by the condition number in the solution. So what this is saying is our solution can be affected by these perturbations if our matrix is ill-conditioned. And to define, so if the condition number is large, so if the condition number is large, AX equals B can be sensitive to perturbations. So in this case, we say that A is ill-conditioned. So if we have a large condition number, then it's going to be sensitive to any kind of perturbation in the matrix, in the vector, in the right-hand side vector. And we call that ill-conditioned. Otherwise, we would say that A is well-conditioned. So if we have a smaller condition number, then of course A would be well-conditioned instead of ill-conditioned. So now let's look at a more practical way to compute the condition number. So if we know the condition number is defined to be the norm of A times the norm of A inverse, Well, let's use the definition of a matrix norm to get a more useful definition for the condition number. Okay. All right. So we were talking about the condition number before, and we were using the norm of A, but I didn't say which norm it was. So let's just define this in the 2 norm. So if I have the 2 norm of A, and the 2 norm of A inverse, then by the definition of the 2 norm of a matrix, then what I would end up with is the square root of the largest eigenvalue of A transpose A over the smallest eigenvalue of A transpose A. And that's because the definition of the 2 norm is the square root of the largest eigenvalue of A transpose A. So here we have A inverse, so we have the smallest eigenvalue of A transpose A. So we can use that to measure sensitivity of a matrix. So if we have an example.
Why is it divided by?
I'm sorry, do what?
Why is it divided by?
Because this is A inverse here. So we have.
Timesing it is actually dividing.
Right. So if we have A1, we have 2 matrices. What we're going to do is these matrices are going to be really similar to each other, but they actually result in very different solutions. And so we'll talk about why that happens. So if our first matrix is 0.7674, 0.6247, 0.0477, 191. So this is our first matrix, A1. And then our second matrix, A2, 0.7581, 0.6358, 0.1113, and 0.0933. So these are our 2 matrices. So in the notes, it's actually already calculated the condition number of both of these. So the condition number in the 2 norm of A1 is just equal to 10, and that's found by this definition of the condition numbers. But the condition number of A2 is actually 10 to the 10th. So this matrix is much more ill-conditioned than this one, but they don't appear to be very different from each other. So let's take a look at their solutions now. So if we have 2 right-hand sides, V1 and V2, they're used respectively to solve each of these systems, then V1 is equal to 0.7662, 0.6426, and then V2, 0.719, 0.7192. So now if we solve these 2 systems where we have A1 times X1 equals B1 and A2 times X2 equals B2, then we get the 2 solutions that follow. So X1 is 0.9894, 1452, and then X2 is negative 1.4522 times 10 to the 8 9.8940 times 10 to the 8. So our two matrices were very similar to each other, A1 and A2, and our two right-hand side vectors, B1 and B2, differ from each other by about 10%, but their solutions are really different, right, in magnitude. That's because this matrix A2 is very sensitive to perturbations, and you can see that by the condition number. So here the condition number was just 10, but in A2 the condition number was 10 to the 10, so we would expect any type of perturbation would throw it off significantly.
Which means the difference between the values of the max and mins are like way bigger. Sorry. The difference between the lambda max and lambda min are way different.
Right.
For A2.
Right. Than for A1. So it's just a matrix that is much more sensitive, therefore it's much more ill-conditioned. So we can't rely on it nearly as much as we can a matrix that is well-conditioned. Okay. Now for any LP norm, so that's including the 2 norm that we were just talking about when we were defining kappa 2, we have 1 over kappa P of A is equal to the minimum from A to A plus delta A singular of delta A and the P norm over the norm of A. So what this is saying is that essentially in any LP norm, the condition number of A measures the relative distance in that norm from A to the set of singular matrices. From A to the set of singular matrices. But because the determinant of A is equal to 0, if and only if A is singular, you would think that the determinant would be a good way to measure the distance from A to the nearest singular matrix. However, it's generally not the case. So measuring the distance from A to the next singular matrix using the condition number is really how we do it most of the time instead of using the determinant. So it's possible for a matrix to have a relatively large determinant and be close to a singular matrix, and it's possible that the matrix has a relatively small determinant and it's not anywhere near a singular matrix. So there's really not much correlation between the determinant of A and the condition number of A. So for example, so A is this really large matrix, but it's upper triangular, so we have one along the diagonal, and everything else is -1 in the upper triangular portion, and everything in the lower triangular portion is just 0. And this is, alright, 1, 2, 3. So A is 10 by 10 matrix. So the determinant of this matrix is really easy to calculate. It's just the product of all of the diagonal elements. So the determinant of A is equal to 1. But if you were to actually calculate the condition number of this matrix, you would get that it's 1,918. So even though, so since it's such a large condition number, that means that A is quite close to a singular matrix, even though our determinant is not close to 0. So if we saw a number that was close to 0, we'd expect to have like 0.00, something like that, but 1 is not as close to 0. So there's not much correlation between the determinant and the condition number of a matrix.
What's considered a large number?
A large number?
Like is 100
Well,
still large or is that small?
Well, I mean, it would, I don't know, I think 100 would be maybe slightly ill-conditioned, but not terrible, right? So if we saw the example over there that had a condition number of 10, which wasn't bad, but that's a good question.
So is it more reliable to look at the condition number as opposed to finding the singular matrix based on
the determinant? Yes. So you want to look at the condition number to see if the matrix, because even if you have a determinant that's really small, you can still have a matrix that's not even close to being singular. Only if your determinant is actually equal to 0 do you have a singular matrix. So if it's close to 0, it doesn't necessarily mean that it is close to being singular. Yeah. Okay, so now that we've talked about the condition number and we discussed
So you're saying the higher the condition number, the closer it is to become being a singular matrix.
yes, the more ill-conditioned it gets.
So is a singular matrix always ill-conditioned?
Yes.
Shall know that already.
So now we've talked about the condition number and how a sensitivity of matrices. We can get into section 5.2 in the notes, and it's labeled Other Krylov Subspace Methods. And this is where we'll begin to discuss non-stationary iterative methods, but we're probably actually going to set everything up today for Wednesday when we discuss the main non-stationary iterative method. So, like I was saying at the beginning of class, we've learned about stationary iterative methods for solving AX equals B, and those come from a fixed point iteration. So now we're going to consider an alternative approach to developing iterative methods that leads to non-stationary iterative methods. So in these non-stationary iterative methods, the search directions are used to progress from one iterate to the next. So,
quick question. Like she was asking, like, if it's even 100 plus, it's not that bad. You were saying. Does that depend on the specific norm? Like in the 2 norm, 100 not that bad. In the infinity norm, hundreds that, or like
No, it doesn't depend on the norm that you're in. It's for any P norm.
any P norm, it will be the same way.
Right.
But then,
Yeah,
like,
so how big can the conditional number be
Until it is singular?
Right.
I'm not sure.
I mean, okay.
Yeah.
1 over infinity is 0. I mean, as it is increasing, the closer you are to be singular.
Right, yeah.
That's
So, I don't know. That's a good question. How large is a condition number? What would the condition number be for a singular matrix? So maybe I can talk about that on Wednesday.
Right, and what number is it, like, sort of like a ballpark when it starts getting bad?
Okay.
Sorry.
It's fine.
What?
I don't know, but we will find out. So what I was saying though is that within these non-stationary iterative methods, the search directions are used to progress from one iterate to the next. So if we want to get xk plus 1, then it's going to be xk plus some constant times the search direction pk. And so we can always choose an initial x, and when we choose an initial x vector, usually we'll choose it to be 0. So we're getting our next iterate from the previous iterate plus something about times the search direction, and that's the whole idea behind a non-stationary iterative method, where pk is the search direction, and it's chosen to be, or it's chosen so as to be approximately parallel to the error. So pk is chosen so can be approximately parallel to ek, the error. And alpha k is a constant that determines how far along that direction to proceed. So just like when we had SOR, we had the parameter omega that just extended Gauss-Seidel in the same direction but further along in that direction. So alpha is the constant that determines how far we go in the search direction. So let's see. So that this new x will be as close to the solution x as possible. So that's how these are chosen. So that gets us into the method of steepest descent. There's some code on the website, and it's called sddemo.m that illustrates how steepest descent works, and actually also illustrates the problems that come from the method of steepest descent as well. So now that we're getting into the method of steepest descent, A is a matrix that's symmetric positive definite. So A is SPD. So we want to consider the problem of minimizing this function phi. So phi of x, 1/2 x transpose ax minus b transpose x. So we want to try to minimize this function phi right here. So if we differentiate, we get we just get ax minus b. We differentiate with respect to x. So
we did b.
Do what?
No.
Yeah. So here we have x and x. So that's plus x squared. Yeah. This is the gradient.
Yeah. Maybe.
Okay. So we just differentiate this function, And so that means that this function has one critical point when ax is equal to b. So now if we differentiate this here, we're going to get the Hessian matrix of b. So if we differentiate this, we find that the Hessian matrix of b is equal to a. So it's like we just took the second derivative. Because a is symmetric, positive, definite, it follows that the unique minimizer of b is a solution to ax equals b. So all of this is just telling us that we can use techniques for minimizing phi to solve ax equals b. So we have that for any vector x sub 0 the direction of steepest descent is given by the following. So it's going to be minus the gradient of phi of x sub 0 is equal to b minus a x sub 0. And so I don't know if we've talked about the residual. We probably haven't talked about the residual vector at all in this class. So the residual is just b minus ax. So here we have b minus ax sub 0. So this is going to be r sub 0, which is the residual. So that's the definition of the residual vector, b minus ax. So this suggests a simple non-stationary iterative method, which is called the method of steepest descent. This is actually, the method of steepest descent is actually from multivariable calculus or calculus 4. Depending on where y'all took it at, might vary in how in-depth y'all went into that. So now we're just going to talk about the method of steepest descent. So the basic idea behind the method of steepest descent is to choose a search direction so we're going to be choosing search direction pk which is equal to the residual. So that's rk equal to b minus a xk. So that's going to be our choice of search directions for the method of steepest descent. It's just the residual vector, which is defined by b minus axk. So now we're going to choose alpha to minimize p of xk plus 1, which of course is equal to p of xk plus alpha k rk just by definition that we talked about at the beginning, we get xk plus 1 from adding alpha k times rk to our previous iterate. So we're choosing alpha k so that it minimizes this function right here. So this entails solving a single variable minimization problem to obtain alpha. So we want to minimize this, so I'm going to differentiate with respect to alpha, differentiate this right here, function phi. So I'm gonna, go back to the definition of phi and just plug this into where we defined phi originally right here. So if I do that, before I even differentiate, then we have 1/2 of xk plus alpha k rk transpose a xk plus alpha k rk. And then this is minus b transpose xk plus alpha k rk. So we want to differentiate all of that with respect to alpha. So let's go ahead and do that. Now, here all of this is multiplied together, so we need to keep that in mind. But this first term, when I multiply it all out, doesn't even have an alpha k, so when we differentiate that term, it would just be 0. So the next term that we have is this times this times this. We differentiate that with respect to alpha. Let's see. We just get rk transpose a xk. And then, let's see, that was for this, and this, and this terms in the middle. And there we end up with an alpha squared, so we still have an alpha in this term, so it's alpha k rk transpose a rk. And then lastly, we want to differentiate everything over here with b. So b times xk doesn't have alpha, so of course that would just be 0 when we differentiate. And then the next term would be b transpose rk. Alright, so now what I'm going to do is rewrite this in a way where it can be condensed slightly. And then after that, we're going to try to solve this for alpha k, because that's what we're looking for. We're trying to find how far alpha k should go along in a particular search direction. And that's what we're doing with this whole minimization process. So what I have with this term here and this term here. I'm going to rewrite this. I'm just going to take the transpose of the whole thing. So when I do that, it's going to become rk transpose b. So I have rk transpose ax k minus rk transpose b plus alpha k rk transpose a rk. So I'm going to pull this rk transpose out on the left, and then I just get ax minus b, but ax minus b, or axk, sorry, is actually the residual, so I can rewrite AX minus B as R. So now we get RK transpose RK minus RK, no, sorry, alpha K RK transpose A RK. Alright, so we're almost there.
So isn't RKB minus A?
Did I miss something?
But you said you wrote RK as AX minus B.
Uh-huh.
So what will that
Oh, I'm sorry. RK, yeah, thank you for pointing that out because I just noticed I missed the negative sign right here. So what that is, R is equal to B minus AX. So so negative R,
is AX minus B?
right?
Yeah.
So no negative sign there. Okay, so now we can finally solve this for alpha. So if we solve for alpha, move to the other side and divide, we get RK transpose RK over RK transpose A RK. And that's our definition, or that's how we define alpha in this method of steepest descent.
We had a plus alpha in the first line, and in the second line we end up having a negative.
Okay, so if we add this to the other side,
Yeah, the
oh,
negative
I'm
before
sorry,
the alpha K.
this right here should be a plus sign. I just wrote a minus sign for some reason, but
Right.
it comes from this term right here, so it's just plus.
Right.
So now that
Okay, yeah,
yeah,
no,
that works.
yes.
Okay, so now that gives us our alpha that we use over here in our non-stationary iterative method. So since A is symmetric positive definite, then the denominator is guaranteed to be positive, so we don't have to worry about that. Another thing, well, let me write down the full algorithm for the method of steepest descent now that we've defined everything. So I think this will be enough room. So what we have for the method of steepest descent is while not converged, so you can just do some convergence check. If you were to write code for this, then the first thing we want to do is define our search direction pk to be b minus a xk, which is just the residual. And the next thing is we define our alpha as we just found it. Let's go ahead and call this R since all of our algorithms is just R. So we have R transpose over K transpose A RK. And then lastly, so now that we have our search direction and our constant, then we can go ahead and compute our next iterative. We could define, well, we would first have to have an initial vector, so we could initialize x to be 0, and then our next, our iteration is defined by xk plus 1 equals xk plus alpha k, pk, or here we call it rk. So that's all you have to do for the method of steepest descent. So it's just going to calculate these search directions and these alphas and then compute each iterative and then update them as it goes each time.
So the only thing you need is just the A, B, next.
So we don't need any new information, it's just, it's got to say differently. So, the method of steepest descent, okay. Okay. So the method of steepest descent is effective when A is well conditioned, but when A is ill conditioned, the convergence is actually very slow. So with steepest descent, what we see happen is the level curves of our function B become long, thin, hyperellipsoids, in which this direction of steepest descent does not yield much progress towards the minimum. So another problem that we have here is that RK plus 1 is guaranteed to be orthogonal to the previous search direction RK, but it doesn't have anything to do with any of the other search directions. So we could have one search direction be orthogonal or perpendicular to the previous search direction, but it could go back in the same direction as the one right before the previous one. So we could have this like zigzaggy effect with the search directions going on. And that's a problem that we want to try to fix with our method that we're trying to build up to. And so you can actually see that zigzag effect demonstrated in this code right here, SD demo. So orthogonality with just the previous search direction isn't really going to help us out and give us what we need. We need more than that. So, like I was saying, each direction, let's see.
Each direction have to be different regardless of that. Like you're saying that, if 1 and 2 are orthogonal, like 3 can be like the same direction as
3
1.
can be parallel to 1, yes.
And that doesn't help. So
No.
Is there a way to make sure that, like all of them are different?
Right, so that's what we're getting. That's what we're trying to get to. Now we're not going to get all of our search directions to be orthogonal necessarily, but well, that's what we're getting to. So, let's see. We've got some time for 10 minutes. So, like I was saying, in this right here, there's only 2 independent search directions are available in a 2x2 case. So the method of steepest descent actually just zigzags the whole way down, so it's not a very effective method, and the more ill-conditioned A is, the smaller each step is going to be too. So now we've kind of seen all the problems of the method of steepest descent, but now that we know what the problems are, we can try to fix those problems to come up with a better method. And we'll get into it just a little bit today, and then finish it up on Wednesday. Alright, so in these in these non-stationary iterative methods, that's what I just had up there, but we had xk plus 1 equals xk plus alpha k times bk. Or alpha k times rk. For the method of steepest descent, the search direction and the residuals are the same thing. So we can, I don't know if it's necessarily good to use it interchangeably, but so our residuals are search directions in the method of steepest descent. But what we want to do is we want to fix this orthogonality problem. So we're going to have a new iteration. And then, of course, we can start with our x to be the initial, or the 0 vector. So this is going to be our fix for this orthogonality problem that we were having with the residuals before. So the residual is for rk plus 1 is equal to b minus a xk plus 1. So now I'm going to rewrite this and plug in what I have defined to be xk plus 1 from right here. So I have b minus a times xk plus mu pk. And then I can go ahead and distribute this and get b minus a xk minus a pk. Okay, so this right here is the residual rk. And we're just rewriting the residual rk plus 1 in a different way. So this is the residual, this part right here is rk minus mu a pk. Alright. So now the reason that I wanted to redefine the residual in this way is because here we're subtracting two vectors that are not both converging to the 0 vector. So if we're subtracting two vectors that are not both converging to the 0 vector, then we're eventually going to get catastrophic cancellation from this subtraction right here. And that's something that we want to avoid. So now we've defined it in such a way where both of these vectors are converging to 0, or should be. So they're both converging to the 0 vector, so now we don't have to worry about that catastrophic cancellation anymore, and we can use this definition of the residual instead. So now our criteria for the method that we're going to, and we're not, let me see what time it is, about 15 minutes. I'm not going to get too much into this today, just so we can get to a good stopping point for Wednesday. But the criteria that we want for this method that fixes this orthogonality of the residuals problem that we had, well, in Steepest Ascent, our residuals were the same as our search directions, but now maybe our search directions can be slightly different from our residuals. So we still want to guarantee orthogonality of the residuals. So we still want to guarantee that, but so it would be nice to guarantee that all of the search directions, or that pk plus 1 would be orthogonal to every single previous search direction. But that goal may not be realistic. But what we can try to achieve is a orthogonality. So that means that these vectors, these search directions, will be orthogonal with respect to matrix A. So if we want to try to guarantee that, then we say the search directions A orthogonal. So we want them to be orthogonal in this sense. Okay. So we call this A orthogonal or A conjugate. So all the search directions are a conjugate. So that's where the method conjugate gradient actually comes from. So if we have from the orthogonality of residuals, I'm trying to decide what's a good starting point. Symmetry there. What?
Just kidding.
So now that I've set up the criteria for the method of, or for this conjugate gradient method, I think that would be a good stopping place, and then we'll actually talk about the A orthogonality of the residuals and the actual conjugate gradient method on Wednesday. So y'all good?
Yeah.
Okay.